In this video, we are going to learn about the general multiplication rule and conditional probability. Let's take a moment to review the multiplication rule for independent events. Now, independent events are events that are not affected by other events. If we have two events, A and B, that are independent, then the probability of A and B, the probability of them both happening, well, that will just equal the probability of A times the probability of B. We just multiply the probabilities. Some people call these AND probabilities. So for example, what is the probability of flipping a coin and rolling a 6-sided dice and getting heads and a 2? So we want the probability of heads and getting a 2. Well, these events are independent because the coin flipping does not affect the dice rolling. So we can just multiply these two probabilities. The probability of flipping a coin and getting heads is 1/2, or 1 out of 2. The probability of getting a 2 on a 6-sided dice is 1 out of 6 because there's only one 2 on that 6-sided dice. Multiplying across the top and bottom, we get 1/12. This is a perfectly good answer there. If you'd like to change it to a decimal by dividing 1 divided by 12, we get 0.083. Let's take a moment to review the deck of cards. Once again, we have a group of face cards, and those include the 4 jacks, the 4 queens, and the 4 kings. The 1 card is commonly referred to as the ace, and we have clubs. That's this top row. We have the spades. We have the hearts. And we have the diamonds. You'll notice that there are 13 clubs in all, 13 spades, 13 hearts, and 13 diamonds. And all in all, there are 52 cards in a standard deck of cards. Now, we'll work through this example, and we're going to refer back to it in just a little bit. So you randomly shuffle a deck of cards and deal 2 cards from the top. What is the probability that you deal a queen followed by a king? Okay, there's 4 queens in our deck of 52 cards, so the probability of getting a queen on the first card is 4 out of 52. Well, after we pick that queen, there's still 4 kings in the deck of cards, but now there are only 51 cards. So the probability of picking a king on that second card is 4 out of 51. Multiplying across the top and bottom, we get 16 out of 2,652. Kind of an interesting number there compared to these. And although we could leave it like that, it would be nicer to change it to a decimal by dividing. 16 divided by 2,652, that equals 0.006. In just a minute, we're going to be talking about this kind of probability ratio in the context of what we call conditional probability. Now, conditional probability is the probability of an event A given that another event, B, has already happened. So this statement here just says the probability of A given B. What we mean by that is that given that B has happened, whereas this would be the probability of B given A. So be on the lookout for this vertical bar in between our 2 events. That indicates we're dealing with a conditional probability. Now, I'll probably be mentioning this again, but in the second statement here, this is really asking us for the probability of B, given this information that we have. So this statement is a statement about the probability of B happening, and the first statement is a statement about the probability of A happening, given this additional information. So back to the card example here. If we have Q representing the event that the first card is a queen, and K representing the event that the second card is a king, let's see, the probability of Q and K, we already showed that that was 4 over 52 times 4 over 51. Well, the 4 over 52, that's the probability of getting a queen. And the 4 over 51, that is the probability of getting a king given that the first card was a queen. So this 4 over 51 was actually a conditional probability. Which brings us to our general multiplication rule. For any two events A and B, the probability of A and B happening equals the probability of A times the probability of B given A. And this works for any two events, whether they are independent or not independent. Remember that previous multiplication rule only worked for independent events. Now, be on the lookout for this type of notation. It means the same thing. So that upside down capital U, that's the intersection symbol, and it just means and. So it means the same thing. So the probability of A and B equals the probability of A times the probability of B given that A has happened, or given A. Okay, let's try it out. You were given some information. We're looking for the probability of A and B. Well, that will equal the probability of A times the probability of B given A. And we know what those equal, so we have 0.61 times 0.47. When we work that out, we get 0.2867. Sometimes things don't line up quite as we would like. Let's take a look at this one. So we want the probability of A and B. Remember that upside down capital U means and, it's the intersection symbol. Well, that would equal, let's see, the probability of A times the probability of B given A. Now notice this is not the information we were told. However, the probability of A and B, that equals the same thing as the probability of B and A. So let's rewrite all this, but using the probability of B and A. Well, that would equal the probability of B times the probability of A given B. All right, we notice we do have information about the probability of B, and we do have information about the probability of A given B. So we don't need this version. So we just need to multiply. And when we work that out, we get 0.2183. All right, suppose that 59% of students surveyed like baseball. I'm going to make a note of that. We'll have B represent the event that a student likes baseball. Of those who like baseball, 69% like theater. Now notice that is a conditional probability because it says, of those who like baseball. So that's the given information. Now notice, this is really a probability statement about the probability of liking theater. So 69% like theater, given that they like baseball. I change that to, notice I changed these percentages to decimals because these probability statements don't work when we multiply percentages. We have to multiply the decimals. All right, we're looking for the probability of selecting a student who likes theater and baseball. So theater and baseball. Let's see, that would be the probability of selecting a student that likes theater by the probability of selecting a student who likes baseball, given that they like theater. Unfortunately, this is backwards again. This is not the information they gave us. So let's switch it around. All right, the probability of selecting a student who likes baseball is 0.59. And the probability of selecting a student who likes theater, given that they like baseball, is 0.69. Work that out and get 0.4071. They asked for a percentage. Let's go ahead and move that decimal place twice and write it as 40.71%. All right, sometimes we need to determine if two events are independent, and there are three ways of doing that. We don't need to do all three. We just need to find one that's satisfied, or just find the first one that's satisfied, and then we can stop. Right, if the probability of A times the probability of B equals the probability of A and B, then we know the events are independent. Another way to tell if two events are independent is if the probability of A equals the probability of A given B. And if we think about that for a moment, that makes a lot of sense. Because if the probability of A equals the probability of A given B, that means B had no effect on A. Or we can tell that two events are independent if the probability of B equals the probability of B given A, because A happened and had no effect on B. All right, let's use this information to determine if A and B are independent events. Well, let's see. If we multiply 0.3 times 0.46, we get 0.138. Well, that was the probability of A times the probability of B, and it did not equal the probability of A and B. So that means events A and B are not independent. Right, here's kind of a trick question. If A and B are independent, find the probability of B given A. Now the key here is noticing that A and B are independent. That means A does not have an effect on B. If A and B are independent, that means A does not have an effect on B. So the probability of B given A would equal the probability of B. And so the probability of B given A would equal the same thing as the probability of B, 0.42. All right, sometimes we need to find a conditional probability instead of the probability of both events happening. Now, we can just use some algebra to divide both sides by the probability of A to get our conditional probability all by itself. And you can either do that before you put in the numbers or after, either way. So the probability of B given A, well, that equals the probability of A and B divided by the probability of A. Now, to remember this, one way to think about it is that this statement here is really a statement about the probability of B, given this information that A has happened. But it's really about the probability of B. So over here, when we're starting with the probability of A and B, you can kind of visualize us canceling out the A's because this is really about the probability of B happening. So we take the probability of A and B, and this isn't actually how the math is happening, but we could think of it as canceling out the A in the top with an A in the bottom. And likewise over here, if what we really want is the probability of A given B, we could divide both sides by the probability of B. And you could do that either before or after you put in your numbers. And we get the probability of A given B will equal the probability of B and A over the probability of B. And to remember what goes in the denominator there, just remember that what we're really looking for is the probability of A, given that this has happened. So over here, we want to keep the A and cancel out the B's. Right, here we're looking for the probability of A given B. And we know that the probability of A given B equals the probability of A and B divided by the probability of B. Because this is really a statement about the probability of A. All right, and we do know what the probability of A and B equals. It's 0.2. And we know what the probability of B equals. And when we work that out, we get 0.541. Now, suppose that in Kern County, 44% of households have a dog, and 29% of households have a dog and a cat. You randomly select a household that has a dog. What is the probability that it also has a cat? So they're telling us the household has a dog. That's the given information. And we're wondering what the probability is that it also has a cat. All right, let's summarize that information. Probability that the household has a dog is 0.44. The probability of having a dog and a cat is 0.29. Now we're looking for the probability that the household has a cat, given that the household has a dog. So remember, here's the question. What is the probability that it also has a cat? So this is a question about the probability that the household has a cat, given this information that the household has a dog. Okay, so this would be the probability of both of them divided by the probability of a household having a dog. And we do have that information because the probability of D and C is the same as the probability of C and D. So that would be 0.29 divided by 0.44, which equals 0.659. And finally, suppose that in a year of 365 days, it rains on 51 days. There's lightning on 20 days. There's both lightning and rain on 5 days. Compare the chance that a rainy day has lightning to the chance that a day with lightning has rain. Because as you've probably experienced, not all rainy days have lightning, and sometimes there's lightning without rain. Right, I'm going to write out our given information down here. We are told that the probability of rain is 51 out of 365. And we are told that the probability of lightning equals 20 out of 365. And we are told that the probability of rain and lightning, which is the same as the probability of lightning and rain, equals 5 out of 365. All right, the probability of experiencing lightning, given that it's raining, well, that will equal the probability of both of those things happening, lightning and rain, divided by, well, let's see here. This is really a question about the probability of lightning. So let's sort of cancel out the R, the raining. So divided by the probability that it's raining. And we do have that information, but it's in fractional form. Let's see, so I'm going to make this fraction bar nice and long here. And I'll put this fraction that we want in the numerator up there. And then in the denominator, we want 51 over 365. Now a fraction can also be considered a division problem. All right, so this would be 5 over 365 divided by 51 over 365. And when we divide by a fraction, we can invert and multiply. So we're going to multiply by the reciprocal of this bottom fraction. So I'm going to start with my numerator, 5 over 365. I'm going to multiply by the reciprocal, 365 over 51. And this is a great method on this particular problem because those 365s cancel, leaving us with 5 over 51, which is a perfectly acceptable answer. But we can also use division to get 0.098. Let's try that one more time. Make sure we got it. All right, the probability of rain given lightning, well, that would be the probability of rain and lightning divided by, this is really asking for the probability of rain, so we're going to divide out the probability of lightning. And using our numbers from down here, we have 5 over 365 divided by 20 over 365. All right, so we're going to multiply by the reciprocal. So we'll start with our numerator and multiply by our reciprocal. The 365s cancel, leaving us with 5 over 20, which is 1/4, which equals 0.25. All right, I hope these examples have been helpful. This is Mr. Ela, signing off.